Math and Beats time, and it's a video on discussing the basic properties of limits. We're also going to prove one of these properties in this video. Let's go. Properties of limits. All right, here's our setup. Let's let k be a real number, and then let's also let limit as x approaches c of the function f of x be equal to L. And let's also let the limit as x approaches c of the function g of x be equal to m. L and m, of course, assumed to be real numbers. Then each of the following properties are true. We're going to state the properties, and then we're going to prove one of them. What are these basic properties? Well, first one here, part A. If we have the limit as x approaches c of that constant k times f of x, then it follows that that's the same as the constant k times the limit as x approaches c of f of x. And since we are assuming that the limit as x approaches c of f of x is L, this is the same as k times L. So remember, we're assuming that the limit as x approaches c of f of x exists, and k is a real number. That means we can just take that limit and then multiply it by k. What's some more properties? Well, right down here, limit as x goes to c now of f plus or minus g of x, which remember this notation is the same as saying limit as x goes to c of f of x plus or minus g of x. Well, then the property says that this is the limit as x approaches c of f of x plus or minus limit as x approaches c of g of x, which is L plus or minus m, depending on if we're adding or subtracting. So this rule that we just talked about in part B, these are really called the sum and difference properties, for limits at least. And the one above that we just talked about, that was called the constant multiplier property. So if we know that the limit exists for f and g at the same location, c for x, then we can add or subtract the limits, and we can also multiply these limits by constants, and everything goes smoothly. Couple more properties here before we prove one of them. This one right here, limit as x goes to c of f of x times g of x. If we wanted to, we could also write that product as f times g of x, just to remind you of some notation. So if we're taking the limit of a product as x goes to c, well then that's the limit x goes to c of f of x times the limit as x goes to c of g of x, which is just L times m here. In other words, if you take the limit of a product, that's the product of the limits, assuming that we know the individual limits exist in the first place, and they're approaching the same x value. That, go figure, is the product property. And then finally, just state this last one here. Limit as x goes to c of the quotient f of x over g of x. Again, we could write that f of x over g of x as f over g of x, just to remind you of the notation again. So if we're taking a limit, x goes to c of a quotient, well, that's the quotient of the limits. That is, that's the limit as x goes to c of f of x divided by the limit as x goes to c of g of x, which in this case is L divided by m, provided that m is non-zero. And that, of course, means that the limit as x goes to c of g of x is non-zero. Please note that the function g could be defined to be 0 at this location C, all we need is that the limit as x goes to c of g of x is non-zero. And you guessed it, this is called the quotient property. So, limit of a quotient is the quotient of the limits, assuming the limits exist in the first place, and the limit in the denominator is non-zero. So those are our 4 basic properties to begin with here. There's a lot of other properties we could talk about, but we'll just keep it to these 4 for the time being. And there's a variety of ways that these are used, especially if you've taken a little bit of calculus. You've likely experienced this. What we'd like to do is approach these properties by looking at it from a analysis perspective and go ahead and try to prove one of them using the definition of a limit. So that's what we're going to do. We are going to look at an example here in which we're going to prove the difference property, and that is we want to prove that the limit as x goes to c of f minus g of x is L minus m. Remember that we are calling the limit as x goes to c of f of x L here, we're assuming it exists, and the limit as x goes to c of g of x, we're calling that m. And then one last refresher, f minus g of x is just the same as saying f of x minus g of x. So we want to prove this limit to be true, this property, the difference property. And we're going to do it by using the definition of a limit. So since we have 2 different limits that we're assuming that exist, limit as x goes to c of f is L, and limit as x goes to c of g is m, we're going to have to make 2 different statements involving our epsilons and deltas, one for each of these. To begin with, since we're assuming that the limit as x goes to c of f is L, then it follows that there exists some delta. Let's call it delta 1 because we're dealing with the first limit here. There exists some delta 1 which is positive such that the magnitude f of x minus L is less than some number epsilon, but we're going to call our epsilon here epsilon 2 for the sake of the proof. As you'll see, it's going to work out nicely if we do it this way. Notice epsilon bigger than 0 also implies that epsilon over 2 bigger than 0. So we're just picking our epsilon in a strategic way, which you're going to see here by the end of the proof. So there exists some delta 1 bigger than 0 such that the magnitude of f of x minus L less than epsilon over 2 whenever the magnitude of x minus c less than delta 1 and positive. That's just using the definition of a limit. And in this case, the limit as x goes to c of f of x equal to L. And we're calling our delta delta 1, and we're calling our epsilon epsilon over 2. Likewise, we could write a similar statement for the limit as x goes to c of g of x, which is equal to m here by assumption. Then, since we know that, we're assuming it, there exists some other delta. Let's call it delta 2, which is also positive, such that the magnitude between g of x, is typo there, magnitude between g of x and m is less than epsilon over 2 whenever magnitude of x minus c is less than delta 2 and bigger than 0. So again, we're choosing our epsilon to be epsilon over 2 here for reasons as we're going to see in a bit. Please note the typo should say g of x there, not f. So silly. All right, so we set up the 2 limits that we're assuming exist, f and g as x goes to c, and we've written them out with respective deltas and epsilon satisfying the definition. Now what we need to show is somehow under these 2 assumptions that this property up there is true. So let's go and try to attack that. All right, now down here, we're going to pick delta in our proof to be the smaller of the two deltas that are appearing in the definitions for limits as x goes to c of f and the limit as x goes to c of g. So they have corresponding deltas, delta 1 and delta 2, satisfying the definition. And we're going to let delta be the minimum of those two. So whatever the smaller of them is, we're going to pick delta to be that. We know it's going to be positive. And now let's suppose that we have that the magnitude of x minus c is less than delta and positive. Then, since we know that delta is less than or equal to delta 1, since we're assuming it's the minimum of delta 1 and delta 2, it follows that the magnitude x minus c is less than delta 1 and positive, and it follows that the magnitude of f of x minus L is less than epsilon over 2. It also follows that for that other delta, delta 2, that the magnitude of x minus c is less than delta 2 and positive, and again, this is a typo, my goodness, g of x minus m in magnitude is less than epsilon over 2. So those are just the two definitions of the limits that we stated above in one statement, and now we're going to pick delta be the minimum value of delta 1 and delta 2. So what? Well, what do we get? Let's go look at the limit as x goes to c of f of x minus g of x. And consider f of x minus g of x. We're trying to show, we're making a claim that the limit as x goes to c of f of x minus g of x is equal to L minus m. So if that's the case, then it better satisfy a definition the way we've constructed our setup. All right, well then, if that's the claim, then by using the limit definition, we have that down here, f of x minus g of x, think of that as just one function, minus the limit, which we're claiming is L minus m. What is that? Well, just rearrange some terms here. That's the same as f of x minus L minus the quantity g of x minus m. So that's just by rearranging the terms inside of our magnitude. And then this next step here, claim is that that's going to be less than or equal to f of x minus L plus g of x minus m. So what's going on there? You probably need to have some kind of reference for this. There is an inequality that is very useful in proofs called the triangle inequality, which states that if x and y are real numbers, then, running out of room here, if we look at the magnitude of x plus y, that's going to be less than or equal to magnitude x plus magnitude y. And you can play around with various x and y values to try to convince yourself that's true. We're not proving it, but it is something that is established. So the same thing will follow for x minus y inside there in the left side of that inequality. And that's what we're utilizing right here. We have on the left of this entire thing, some quantity f of x minus L minus some other quantity g of x minus m. And by a triangle inequality, that should be less than or equal to the first part, f of x minus L in magnitude, plus second part, g of x minus m in magnitude. But because we know that f of x minus L is less than epsilon over 2 by our first definition, and we know that g of x minus m is less than epsilon over 2 as well by the second definition, well then, this entire quantity is less than epsilon over 2 plus epsilon over 2, which is epsilon. Hence, by picking our delta appropriately, we get that this entire quantity on the left here that I'm circling, f of x minus g of x minus the quantity L minus M is less than epsilon. Hence, what do we show? No matter which epsilon we pick, for all positive epsilon, if we have that magnitude x minus c is less than delta, which is assumed to be the minimum of delta 1 and delta 2, some positive delta, then f of x minus g of x minus the quantity L minus M, that's going to be less than epsilon in magnitude, which tells us that we have now proven the property. And that is, limit as x goes to c of f of x minus g of x is the same as the limit as x goes to c of f of x minus the limit as x goes to c of g of x, which is just the number L minus the number M. So it's kind of a involved proof because we have chosen our epsilons and our deltas very appropriately so that we get the result that is anticipated. And there you have it. We proved the difference rule property for limits. Very similar proof can be done for the addition property, almost exactly the same proof. And those other two properties, the product one and the quotient, those are a little more involved, but they involve picking epsilons and deltas in a way that is, clever, if you will. So anyways, that is the video on just stating the basic properties of limits, the arithmetic properties, if you will, and also walking through how to prove at least the difference property for these limits. More videos to come on proving stuff within the calculus realm. All right then, until next time. Bye-bye.